This next section of Chapter 3 involves a lot of calculations and equations, as you can see here. We're going to learn how to determine molecular formulas from empirical formulas. We'll be able to calculate the mass of water in an ionic compound, so a hydrate, which we learned how to name in previous chapter. And we'll do some conversions, starting with grams or mass of a reactant, going all the way to grams or mass of a product. And in order to do that, we first need to convert to moles and do a mole ratio. First, let's look at percent composition. The equation is shown at the top of the slide. So for percent composition, what this allows us to do is when given a compound such as silver 1 nitrite here, we can use the equation above to figure out what percent of that compound is made up of just silver, or what percent is made up of just nitrogen, or what percent is made up of just oxygen. And the nice thing about it is once we figure out the percents of each, when we add them together, they should equal 100%, or very close to 100%. So it might be slightly less or slightly more than 100, depending upon what periodic table you use. Because as you'll notice, we're using the molecular weight of the element in the equation. And depending upon the periodic table, they might round it slightly differently, not allowing you to get exactly 100%. So I do want you to be aware of that. But it should be very close to 100 if you did it correctly. Now, how are we going to do this? Well, first of all, you can see that we need the molecular weight of the compound as a whole, which they have given to us, and that is 153.874 grams per mole. Notice that is present in the denominator of the equation, so it's going to go on the bottom of that fraction. So how are we going to solve for this? Well, if we were doing silver, for example, trying to figure out what percent of that particular compound is made up of just silver, we would need to take first the number of elements, atoms of silver. So that's the first part of the equation, as you can see above. And looking at silver, there is no subscript after it. So we assume it's a 1. That's what this ratio is telling us. There's just one atom of silver. So we would take 1 multiplied by whatever the molecular weight of silver is, and we would find that on the periodic table. And then we would divide that by the molecular weight of the entire compound, which is 153.874. If they did not give that to you, you would need to solve for the molecular weight using the procedure that we explored earlier. Don't forget to multiply it by 100 to get it into a percent. Now you would do the same thing for every other element present. So if you were trying to figure out the percent of just nitrogen in the compound, start with the number of atoms of nitrogen present, which we can see from the ratio and the chemical formula that it is just 1. Multiply that by the molecular weight of hydrogen, which is around 14.01, I believe. You have to check your periodic table to make sure. And then divide that by the molecular weight of the entire compound. So notice the denominator is staying the same for each of these calculations. It's just the numerator that's changing based off of the element we're exploring. The last element present in this particular compound is oxygen. So for oxygen, notice there are 2 oxygen atoms. So you would multiply that by the molecular weight of oxygen, which will be either 16 or 15.999, depending what periodic table you're using, and then the same denominator as usual. So once you solve for those, you'll see that there is approximately 70.1% of silver, 9.10% of nitrogen, and 20.8% of oxygen. Now you can try the next one on your own. I do want to note on the next one that this number 2 that's on the outside of the parentheses, that needs to be factored inside everything that's inside the parentheses. So what I mean by that is there are 2 chlorines, and it looks like there's going to be 8 oxygens, because you would have to take that 2 and multiply it by the subscript on oxygen, which is 4. So 2 times 4, that's how they got 8 oxygens here. Okay, so whenever you have parentheses around a polyatomic, you need to take the number outside of the parentheses and distribute that to everything inside of the parentheses. So go ahead and pause, try to solve that one on your own. using the procedure I described above, and your answers are shown here. Here are some practice problems. You are welcome to try on your own. We will also be going over these in lecture before continuing on with Chapter 3. You'll notice each of these problems ask for just one of the elements in the chemical formula. We're not solving for all the elements. So it's just one calculation for each. Next, we're going to look at empirical formulas. So an empirical formula is not the same as a chemical formula. Chemical formulas are what we've been describing so far. Chemical formulas are what's present in the chemical equations that we've been looking at. So what's the difference? An empirical formula gives the smallest whole number ratio of the elements in the compound, and those don't necessarily reflect the actual numbers. So this is essentially the reverse of what we were doing in the last calculations. So you'll notice for the steps that we see here to figure out chemical formula, step 1 is starting with a percent. And that's what we just did before. We took the formula itself and we figured out what percent of each element was present in that chemical formula. So now we're going to go the opposite direction. We're going to be given the percents, and we're going to have to take those percents and come up with what the chemical formula is. But it's not going to be the true chemical formula. It's going to be the lowest whole number ratio of the chemical formula, and that's why it's referred to as empirical. So how do we do this? Well, I said we start with a percent. So you change that percent to grams. How do you do that? Literally erase the percent sign and add a G. Easiest step there is out of all these steps. Erase the percent sign and put a G by it for grams. Okay, because remember, we said that all of the elements present should equal up to 100%. So since it equals up to 100%, we can change those percents just to G's. Step 2, we're going to take the grams that we've now converted it to simply by erasing and replacing with a G, and we're going to convert it to moles. Remember, anytime we need to convert between grams and moles, we'll need the molar mass or the molecular weight of a compound, because the molecular weight of compounds are measured in grams per moles, which is a conversion factor to convert between grams and moles. So that's going to get us there. Step 3, divide by the smallest mole. So you'll notice in step 2 here, we converted all the gram amounts to mole amounts. So we'll have mole amounts for each element present in the chemical formula. Whichever mole amount is the smallest, we're going to divide all the other mole amounts by that number. Last but not least, multiply to get a whole number. If we already have a whole number, this step is unnecessary. It's only if we do not have a whole number or a number that's close to a whole number. Let's do a practice problem. We have a molecule with the following composition. Notice it's given to us in percents. Also notice if you add those percents together, it's going to be very close to 100. They're asking us to solve and figure out what the empirical formula is going to look like. So formula with its lowest whole number ratios. The steps are at the bottom of the page. Feel free to pause if you want to try this on your own. But we start with the percents, then we'll change it to grams just by replacing those percent signs with grams. We'll use the molecular weights to convert to moles and go through the rest of the process. First step, changing those percent signs to G's. Next step, converting between grams and moles. So for calcium, we would take the gram amount that we have changed from percent, 54.1, and we're dividing it by its molecular weight. So this 40.078, that's the mass of calcium as found on the periodic table. So that's where that number came from. The reason we're dividing by the molecular weight of calcium is because we need the grams to be on opposite sides of this horizontal line so they cancel, leaving us with moles. We do the same thing for oxygen and hydrogen using the mass of oxygen which is 16 grams per mole, and the mass of hydrogen, which is 1.008. Or if your periodic table might say 1.01 if it rounded differently. So now we have all of the amounts in moles. The next is to figure out which one is the smallest and divide. So looking at these numbers, I see that calcium has the smallest, 1.35. So that means we're going to divide all three of these by 1.35. Doing that, dividing 1.35 by 1.35 gives us a whole number of 1. For oxygen, 2.7 divided by 1.35 gives us 2. And then for hydrogen, it's going to give us a number slightly less than 2, but it's really close to 2. So we just round it up to 2. So we have whole numbers for all of them, meaning for this particular one, we can skip the last step where we multiply to get a whole because we already have whole numbers. So these whole numbers that we have, these are going to be the subscripts of our empirical formula, meaning we're going to have 1 calcium, we're going to have 2 oxygens, and we're going to have 2 hydrogens. So the chemical formula then becomes CaOH2. Now notice that they have the OH in parentheses with the 2 on the outside, indicating there are 2 oxygens and 2 hydrogens. The reason they put parentheses around the OH is because they recognize that OH is a polyatomic, the hydroxide ion, and so they put it in parentheses to indicate that. So this would be the correct empirical formula for this practice problem. The next practice problem has 4 different elements in it. So these 4 different elements are carbon, hydrogen, nitrogen, and oxygen. So they've given us the percent composition of each. So we want to go ahead and go through the process. So the first step is to take that percent, erase it, and write grams. Next step then is to find the molecular weight of each element present and divide the gram amount by the molecular weight of each element, and that will give us the molar amount. So for carbon, divide by 12.011 its molecular weight, hydrogen 1.008, so on and so forth. So now we have the molar amounts. So our next step after finding the molar amounts is to figure out which one is the smallest and divide the rest by the smallest mole amount. So smallest looks like nitrogen at 0.6797. So we want to divide all of these numbers by 0.6797. When we do that, it looks like we have a whole number for all of them except for oxygen. So I'm going to go ahead and circle oxygen. Notice oxygen's at 2.5, so right at a half amount. So we do need to do this final step of multiplying to get a whole number. And you always want to multiply by the lowest whole number possible, right? If we multiply by 1, that's not going to help us get a whole number, so we move up to 2. So if we multiply 2.5 times 2, that should give us 5, right? But we can't just multiply oxygen by 2. We have to multiply all of them by 2. So the whole kit and caboodle. When we do that, we get carbon for a total of 14, hydrogen a total of 18, nitrogen a total of 2, and then oxygen a total of 5. So these numbers that are shown here, these are the subscripts after each one. So C sub 14, H sub 18, N sub 2, O sub 5 for an empirical formula shown highlighted here. How do we represent empirical formulas as molecular formulas? So how do we get there? So remember, empirical formulas were the lowest whole number ratio of the formula itself. It does not necessarily represent the chemical or molecular formula. So we first, of course, need to know what the empirical formula is, and that's what we just did on the previous slides. Next, we need to determine the molar mass of the empirical formula. And that we can calculate using our skills to calculate molecular weight, where we take how many atoms of each element are present, multiplied by the molecular weight of those elements, and adding it all together. Step 3 is determining the ratio of the mass, and that's what the equation above is. So we would take the molecular weight of the compound in the numerator. Now the molecular weight of the compound, that's going to be given to you in the problem. That is not something you'll have to solve for. They will give that to you. So that'll be in the numerator, and the denominator is going to be the molar mass of the empirical formula. Now this might not be given to you. They might just give you the empirical formula itself, and you have to calculate the molar mass of it. So dividing these two should give you a whole number. Whatever that whole number is, you're going to use it in step 4, which is what you're going to multiply the empirical formula by. So let's look at a practice problem. What is the molecular formula of a compound with an empirical formula of CH2O and has a molecular weight of 180.156? Okay, so they gave us the empirical formula, which is the lowest whole number ratio of the formula. We will need to use this formula to figure out the molar mass of the empirical formula, because that's what we need for part of our equation. Now they gave us the molecular weight of the compound as a whole. That's the part that goes in the numerator. So we have all the information we need. We just need to go through the steps. So determine empirical weight will be our first step. Then we'll determine the ratio using the equation on the previous slide. By the way, that equation is not given to you on the exam. You just need to memorize it, know how to use it. And last but not least, we'll use the whole number we get from the ratio of elements to determine the molecular formula. So the empirical weight of CH2O, when calculating it out, is 30.026. Make sure you calculate that on your own and that you know how to calculate it. Now, as for the ratio, notice we put the molecular weight of the compound as a whole in the numerator, that 180.156 that they gave us in the equation, and we divide it by the empirical formula weight that we calculate on our own. And we get close to a whole number. It doesn't show up to be exactly 6, but it's very close. So this is the whole number that we're going to multiply the CH2O by. So it means we're multiplying by all the subscripts. So that means we'll have 6 carbons, 12 hydrogens, and 6 oxygens to get C6H12O6. Looking at hydrated compounds, we're going to learn how to name them, but first we need to know what a hydrated compound is. So a hydrated compound is an ionic compound that has water molecules trapped in its crystalline structure. So the nice thing about naming these is it's not entirely new, because we're going to name the ionic compound portion how we've already learned. So if it's a main group ionic compound, we name it with the metal first, and then the non-metal portion, we would end with an IDE ending. Or if the non-metal portion was a polyatomic, we would use the polyatomic ending. The difference now is going to be the water part. So to represent the water portion, we need to use a prefix indicating the number of water molecules that are trapped. So that's why the prefix table is over here to remind us of those prefixes, same prefixes that we used when naming covalent compounds. So we use a prefix for the water molecules, but instead of saying prefix water like mono water or di water, we don't use the term water. Instead, we use the term hydrate, as you can see in the example below, hydrate. So the example shown below is NaCl, and then there's a dot indicating that there are 3 water molecules trapped within its crystalline structure. So we name the ionic compound just like how we would normally. So since sodium is a main group metal and not a transition metal, we don't need the parentheses with the Roman numerals indicating the charge. So we just write sodium because we know its charge is always going to be a +1 since it's an alkali metal. And then chlorine becomes chloride. And then for the water portion, we use a prefix to indicate how many waters. Since there are 3, we are using tri. And then to indicate the water, we use the term hydrate. So for hydrated compounds, if you are given the chemical formula of a hydrated compound, like on the previous slide with the sodium chloride trihydrate, you need to be able to name it. But you also need to go in the opposite direction. So if you are given a name or the amounts, you need to be able to come up with the formula itself. So this slide is showing the steps, and then on the next slide, we will look at an example problem using the steps. So for step 1, the problem will usually give you the mass of the wet compound with the water in it. Then it will say something about the wet compound being dried in an oven or with a Bunsen burner to get all the water off. Then it will give you the mass of the dry compound. So you'll have 2 masses of the compound, one with the water molecule stuck inside the crystal and one where the water molecules have been heated off. So you'll need to subtract those 2 to figure out the mass of the water by itself. Because that's the only thing missing between a wet compound and a dry compound is the water. So when you subtract those 2, you'll get the mass of the water. Then step 2, you're going to solve using similar steps to the empirical formula. So instead of starting at percent, since obviously we're looking at masses, right, from the previous step 1, all of them are masses, so you'll be starting with gram amounts instead and going through the process to moles, dividing by the smallest mole number, etc. So in this example problem, it says you're isolating a compound of magnesium sulfate from a water-based liquid. You are weighing the substance to get a total weight of wet. So this wet magnesium sulfate, that is the magnesium sulfate with the water in it, 76.60 grams. You let the compound dry in a 100-degree oven for over 30 minutes, meaning you're driving off the water molecules. The compound is weighed again to determine the dry weight. So the dry weight with no water in it, so just magnesium sulfate by itself, is 25 grams. So 2 questions, weight of the water and the formula and name of the hydrate. So for the name or the weight of the water, that is a simple subtraction of the 2 numbers circled. So 76.6 minus 37.25. So let's look. Mass of the wet, mass of the dry. Notice they also have, for what we know, the molecular weight of not only the ionic compound, magnesium sulfate, but of the water itself. So why do they have the masses of both of those? Because you'll notice one of the steps is to convert between grams and moles. And in order to convert between grams and moles, we need to know molecular weight because the molecular weight units are grams per moles and it can convert between the 2. So that's why those are listed there as a known factor that will help us solve. Roadmap. First, to figure out the mass of the water, subtract the 2 masses. Then we're going to determine the ratio of water to the compound. That's why we have to get it into moles, because when we're comparing ratios, we can only compare ratios if the units are in moles. We cannot compare ratios when they're in grams. So it has to be in moles first. So that's why that step is so important. And we'll see that in stoichiometry as well towards the end of this chapter. So always convert to moles when you're comparing ratios. And then last but not least, determining the name. So first step, was subtracting those two numbers, those two masses, so that we could figure out the mass of water by itself. So 39.35 should be the mass you got for water. Next, we convert both to moles. This is that grams moles step right here. So for the magnesium sulfate, we convert that to moles by dividing by the molecular weight of magnesium sulfate. That way grams and grams canceled and we're left with moles. Water, same thing. We take the mass of the water by itself, which we calculated up here at 39.35, and divide it by the molar mass of water, which was 18.016, to get the molar amount of water. Next step then is to divide by the smallest mole amount. So to divide by the smallest mole amount, we're comparing the two moles that we just calculated, which is 0.3095 and 2.184. So which one is smaller? Well, 0.3095 is smaller. So we divide both of those mole amounts by 0.3095. So we're going to get a whole number of 1 to represent the ratio of the magnesium sulfate, and a whole number close to 7, looks like we're rounding, for the water. So that means for every 1 molecule of magnesium sulfate we have, we're going to have 7 water molecules trapped in its crystalline structure. So the formula is then going to be 1 magnesium sulfate. Notice we don't put the 1 there since there's only 1 of them, it's assumed, per 7 of the waters. That's why we have 1 MgSO4 times 7 H2O. To name it, we name the ionic compound first, magnesium sulfate. And then for the water molecule, water molecules in this case, we use a prefix, and for 7, the prefix is hepta. And then to represent the water molecule, we use the word hydrate. So magnesium sulfate heptahydrate. Notice this time we did not need to multiply to get a whole number. Sometimes you will, sometimes you won't. Just be aware of that.